Hello, everyone. Today's session, we focus on Ethernet switching basics. I think that module should be around 7 out of 20 something, 23. With Ethernet switching basics, we'll focus on the most common protocol uh, at layer 2, which basically is what layer 2 switches are based on. So we'll take a look at what Ethernet as a protocol is, what defines its functions in layer 2 switching, introduce what a MAC address is, structure of a MAC address, why you have a MAC address and an IP address, which is a layer 2, layer 3 address, both assigned to hosts. And we'll basically look at how switching happens, the process um, of switching in networks. So I think in short, when we talk of Ethernet switching, we are talking of how information is processed in the layer 2 of our OSI model. Objectives of the course will be to describe the basic concepts of an Ethernet network, distinguish MAC address types, get familiar with working process of a layer 2 switch, and structure generation process of a MAC address table. Ethernet is the most common communication protocol standard existing, used by existing LANs, defining cable types, signal processing methods used in LANs. An Ethernet network is a broadcast network built based on the CSMA CD mechanism. Right, so basically, early communication, yeah, we use what we call we use an algorithm which we call the collision detection algorithm. We also have another one, the collision avoidance for those vanenge vanofamba nekuverenga. This one is the one which is used in wired networks, including Ethernet. We have another one, the collision avoidance, which is used in wireless. Another standard, wireless standard, IEEE 802.11, is still in use to this day. Right. Early technologies, I think we used, I think we used, the bus topology. We discussed my type of topologies, I think, early in our sessions. With the bus topology, it's a type of topology where we have a shared medium, what we call a shared medium. So if you look at early Ethernet, shared medium is this medium where every device in the network is attached to that shared medium, meaning if there is need for communication uh, from any of the hosts from within that shared medium, then inengeta pass through the shared medium. Problem now being if multiple devices try to access that shared medium at the same time, there will be more collisions. So this basically led to introduction here, the algorithm here, collision detection, which was to avoid more collisions. So every time a host is trying to use the medium, they will send a message to the shared medium, basically saying, I need to access the medium. to check if there is anyone else making use of the medium, any other host making use of the medium. Then pakatika collision, there will be some time yekuti my devices will not be sending any information so that they avoid further collisions mamwe anokwanisa kuitika within the shared medium. I think briefly that is what defined this algorithm collision detection. It was used to avoid collisions, early technologies from bus topology. We can call that early Ethernet. Now switch to the technologies that we are using now. We no longer have with wired networks. We no longer have collision detection. We still have it, but we are no longer using it. With my introduction in my switch, where a switch, a layer 2 device, can be used to separate my collision domains, what we call my collision domain. With this type of network, Irabai, we had one collision domain. By collision domain, defining a domain where if multiple devices try to access a medium at the same time, then panic collision. So PANAP is one collision domain because if any of the hosts try to access the shared medium, then there'll be a collision. On this side, we have a device that runs a switch, basically separating my collision domains with each and every port switch representing a collision domain. So you see it in the collision domain 1, 2, 3, 4, 5, meaning every host run a collision domain run. It means there is no longer need yokushandisa the algorithm collision detection because a host is not sharing its collision domain with any other host. So I think that's the transition iripo from early technologies, the Ethernet, going into my switched networks arikushandiswa these days. Keywords I think to take note of is of my algorithms zedu recollision detection, then definition here collision domain at this stage. Right, I think this is what I've been covering. My collision domains edu, I've already defined them. A set of nodes connected to the same shared medium, all nodes in a collision domain competing for the same bandwidth. Packets sent by a node can be received by other nodes. So basically with a collision, within the same collision domain, send a message from any other host, all the other hosts in that network will sort of be forced to listen to that message. That is what defines a collision domain. Right, from there we can define a broadcast domain. The entire access scope of a broadcast packet, which is also called a broadcast domain, or hosts in the same broadcast domain can receive broadcast packets. With a broadcast domain, we now define a domain where if a broadcast is sent, every device within the same broadcast domain receives the message. So when we talk of a broadcast domain, you realize that even if per network here we have multiple collision domains, a layer 2 device here which allows us to switch separates my collision domains, but the broadcast remains only one broadcast domain. Chinozokwanisa separate my broadcast domain in our case is probably addition here device, layer 3 device in a router. So I can then create another collision domain like this. Broadcast domain, I mean. If this is broadcast domain 1, router edu layer 3 device can be used to separate my broadcast domains edu. So difference between my collision domains, my broadcast domains, can be separation yayo, my collision domains, we can use a layer 2 device with every port per layer 2 device representing a separate collision domain. Then my broadcast domains, we can have a layer 3 device, a router, basically separating are our broadcast domains. On traditional Ethernet networks, multiple nodes on the same medium share a link. Then a switch forwards broadcast packets or interfaces. A switch does forward a broadcast packet. However, a router by default does not forward a broadcast packet. So in this case, can a broadcast domain is if host A sends a broadcast, it means everything within this domain will receive the message. Broadcast iraende kunoenda kune rimwe broadcast domain by default because routers by default do not forward those broadcast domains. I think a lot said collegiate domains and my broadcast domains. We have the Ethernet NIC. By definition, in NIC being a key component that connects a network device. So when we talk of an NIC, we can call it hardware. It's hardware that allows our computers to connect to a network. So this hardware can be in the form of let me see. On your computer, connect the Ethernet cable, there is a port riripo rinopinda Ethernet cable. That port is directly connected to the NIC, which is the hardware. In computer, if you're using a laptop or if you're using a desktop, that port is directly connected to the NIC. NIC don't allow it's sort of the interface between the network and your computer. That is what it defines in NIC. And I think with that, I've defined these two things, a port and an NIC. We also have wireless NICs, which allows us to connect wireless networks to our computers. So with this one, the Ethernet in a port it's a wired NIC. It's Ethernet cable yako. We also have on our laptops, it's not visible, our wireless NIC, but kana riripo, that is the one which allows you to either on Wi-Fi, be able to connect to the internet via the Wi-Fi. Kana pasina, I think you've seen my sort of to my USBs, ka wireless NIC, ka USB, no connected at the back of your desktop, which then allows you to get access to the internet. To my antenna. Those are some forms of my NICs that we can have. My computers edu they do not have. I'm yet to see a computer in a fiber NIC, but some of my network devices edu my switch. You can have a port to connect a fiber. At the back of that port or within the device, you can see NIC, many different type of NICs from wired NIC, wireless, then obviously fiber. Anything, any interface which allows us to connect to the internet defines what we call the network interface card. Ethernet frame, then frames are used by Ethernet technology, being referred as Ethernet frames. Ethernet frames come in two formats, Ethernet 2 and IEEE 802.3. Right. When we discuss the OSI model, I think we discussed something to do with my PDUs or protocol data units. And we said in the application layer, in the upper layers, we have a PDU ready on the data. Then we have my segments. Then we have packets at layer 3. Then we have my frames at layer 2. And at the end, we have my bits, which basically represent the information to be transmitted in the physical layer. When we are talking of Ethernet as a protocol, we mostly focus on layer 2, although Ethernet also defines my standards at layer 1. In this case, we're just focusing on layer 2. So when we talk of layer 2, we talk of my frames being the protocol data unit at that specific layer. Frame or a PDU, let's say, a structure. Structure defined by a number of fields. In this case, structure edu, it can be simplified as having yet not a header, then having our information, let's just call it data, then a trailer. So head and a trailer yedu, panapa will be our destination and source MAC address. Kuskapana. Then this is our information, is a data. Then everything is after this. This is our trailer. My fields that now to the destination MAC address, yangazi DMARC, which represents the information with the source, with the type or length, depending on these two types of my frames at now. Then we have our user information here. And at the end, turn to FCS frame check sequence, which is used for checking former errors, data integrity, which is used for data integrity. Right. Difference between Ethernet 2 and Ethernet 2.3 being this one is the original version. This one. Ethernet 2, no, this one is the original standard here. That's the original standard of the Ethernet frame, where panapa, soon after the source MAC address, you have the length of the Ethernet frame Irako specified. And panapa, you have two more fields, LLC and SNAP, where LLC basically contains DSSAP, destination service access port, then also contains the source service access port. With the destination service access port indicating the upper layer protocols which should be receiving the frame, and the other one representing the upper layer protocols where we are sending on the sender side basically. And per snap up, you can see doparoso ya type iri panapa iyi. Type representing the protocol ratichashandisa in the upper layers. Difference between those two with the latest technology is just a simplification. We no longer have this specified field LLC. We no longer have it specified, only taking note of the type soon after our source MAC address. So with the Ethernet frame, we have two more types, EMA formats. What we use these days is this one here, which is sort of a refined format from the standard OG Yangatinaris. It's very important to take note of my sizes. Let me see. My sizes EMA fields edu. It's very important to take note of my sizes EMA fields edu. My numbers are up. Here we have a source MAC address here. We're having 6 bytes. This is 6 bytes. 6 bytes, 6 times 8, that's 48 bits. MAC address in a 48 bits. That's why we have 6 bytes here. Our source MAC having the same size, 6 bytes. Then our type, the type of layer 3 protocol we are using, this can be a IP, can be ICMP. It all depends on the type of protocol that we're using there. 2 bytes. Then user data rate anywhere between 46 to 1.5, which is what we call the maximum transmission unit. Then our FCS having 4 bytes. Importance of this, it defines the size the Ethernet frame. You're going to realize Panama numbers are up. Length reframe rate can be anywhere between 64 and 1518 bytes. My size is why they are determined by my numbers are up. What do we mean when we say total length is between 64 to 1518? It basically means for an Ethernet frame, kuti rinzi rakakwana, it should be between this size. With that, we introduce my cases ekuti is less than 64 and it's more than 1518. Can I read more than? That's a problem. Message size is very important in communication. That's why we have things like segmentation, fragmentation. My messages and my larger size being broken down. Why? Because size is very important to my messages. Message ikakurisa stereo, that could be an issue, but transmission, not to the bandwidth yakawanda, so it's broken down. So message Ethernet frame rate will get more than 1.518. Not sure what they call it, Huawei, but it's called a giant. This is an error. My error message is SI, giant can read more than, can read knock less than 64 bytes, ring a rant, error foot here. So you could have my messages ako, you could have message yako having my extreme cases are less than 64 or more than 1.518. My error information message you will not get to the, it will get to the destination, but it will be detected as actually it won't get to the destination. My frames and my errors. So message size here is very important and it should be 64, between 64 and 1518. Then there is need of understanding could every field panapa. What does it represent? I think these two are very simple. I've gone through that. The type I've said is the layer 3 protocol that is being used. Panozosvika frame rate per layer 2, then user data rate, which user data. FCS, this is integrity check. That's the field which is used for integrity check, basically. Then frame format. Anything. Right. I might miss one or two few things, but I think that's the importance unity war. I'm trying to figure out did I miss anything here that is important, but negative want anything brain zangu. We go to the MAC address. Media access control address uniquely identifying an NIC on a network. Every NIC, we've defined an NIC already, the interface between the network and a device, a networking device. Every NIC has what we call a MAC address. A MAC address, also known as a physical address. At layer 2, every interface NIC has a MAC address. Each NIC has a number that is a MAC address used to identify itself, just as each person has an ID card number to identify himself or herself. That is what defines the MAC address. Let me see, IP versus MAC address. At layer 3, we have another identifier, the IP address. Characteristics of IP addresses: unique, changeable, assigned based on network topology. Then the other one, MAC address, unique, cannot be changed, assigned based on the manufacturer. Why I have two my unique identifiers to the same host or a host? Very difficult term to understand, my host. But ideally, how I put it, an IP address, if I have a network, so if I have two more networks, something like this, two remote networks. So network A and network B. If I want to communicate between remote networks, I use layer 3 addresses. I use my IP addresses because at layer 3, my IP addresses are defined by the networks they belong to. It's like saying network yangu iHarare, network yangu iBulawayo. So kana ndiri kuda kusenda information from Harare to Bulawayo, I first identify the network. Ndika-identify network yangu, ndakuziva kwandiri kuenda at least, then I can then further say what's the physical address yepandiri kuenda. Probably ndiri kuenda kuBudiriro. That sort of is the analog, yeah, the physical address or the MAC address. So I use the IP address to identify the network, then I use the MAC address to identify the physical address of a device. So IP is like saying ndogara kuHarare, but to be more specific, ndogara kuBudiriro, that would be the MAC address. So at layer 3, then I identify IP, then kana IP yashanda, I go to layer 2, ndo identify our MAC address. Why both of them are used? There are scenarios dzekuti you can have different MAC addresses. No, you cannot have different MAC addresses. You can have different IPs. So ndikaenda device ndiri munetwork muno, my IP address will be defined depending on the network B. Ndikabuda munetwork ndikaenda to another network, IP address yangu will change because of network yangu yachange, location yachange. Ndabuda muBulawayo ndaenda muGweru, zviro kuti IP yangu yachange. So an IP address is dependent on the network where a device belongs to. However, the physical address is dependent on the NIC. As long as device yangu iri muno in the same NIC, it means even if ndikashifta kuenda kunoko, my MAC address remains the same. That's the importance. So ndinoshandisa mama addresses SR2. In the case yekuti ndikachinja network, I can still be identified by the MAC address, by the physical address. I know logic wise, zvekuti Budiriro zvatochinja, but that's the idea around why we have my layer 3 devices and my layer 2 devices, and why they are used, both of them. So to link them, probably you've passed through a protocol known as ARP. That's the importance of that protocol. It basically establishes a relationship between the IP and the MAC address with the ARP table showing us the mapping yekuti IP address kana iri yakati, what is the MAC address. Very important for communication yedu, that mapping. MAC address representation, MAC address yedu ine 48 bits. 48 bits. So for that divide, we're into six uh, my groups. Let's call this one six. So this is group number one. This is group number six. 6 while adding to my hexadecimal values. So 0 uyu, 0 uyu. Those are two hexadecimal values. This is one another hexadecimal. This is E another hexadecimal value. They are separated by a colon. So in between upper something like this or a separator like this. It all depends with the type of notation you are shandisa. So basically, IP address here do 48 bits, 6 bytes, tichishandisa my hexadecimal values. Composition and classification. MAC address here do in a 3 bytes. Yet not the OIU, which is basically the part which is assigned to a manufacturer by IEEE. IEEE being the organization responsible for my standards and one day, including the one Ethernet. So 3 bytes per 48 per 6 bytes there is 3 bytes is it's assigned to manufacturer or by IEEE. So basically you can identify my brains. You can identify my brains using the MAC address. Just a minute. Right. So I was saying you can basically identify the type of brands or manufacturer by looking at these 3 bytes. You don't know, I don't even know one brand. I know in theory, but I think that's something you could look at to identify to brands. Or you check it say by looking at the first 3 bytes, you can identify with the manufacturer with this device in the end. Then the other part, the CID, is then the manufacturer akupa this part. Manufacturer and this one is given by the manufacturer. So MAC address here is unique in the sense you go to one, the OIU is assigned by IEEE to the manufacturer. Then the other part, manufacturer OPA specific devices. That's basically the composition, MAC address here. Then when you talk of classification, let me see. Is this popping in of the way? MAC address classification, we have I don't know my unicast MAC address. We have multicast MAC address, broadcast MAC address, unicast 1-to-1 if you're sending to one end device, multicast if you're sending to a group of devices, then broadcast when you're sending to all devices within the same local area network. A unicast address is identified by bit bit number 8 out of 48 rinenge 0. Kana 0, it basically means that's a unicast MAC address. Then on the other end, kana 1, that's 8th bit, it basically means it's a multicast MAC address. Then if all the bits are variables 1, it means address here e broadcast. In a gap, would I get something like this? One address in my F like this, that basically means it's a broadcast address. I always say, can always send that to one device unoshandisa one address. Kana uri kusenda to all devices in the network, unoshandisa one address as well. You don't use multiple addresses. You don't use all addresses of the devices within that same network. You still use one address. An address here shondo irapai. That is what we call the broadcast address. Classification, composition, Unicast Ethernet frame. I think we've defined this one. 8th bit error rinofana kunge riri 0 and frame rinoenda to one device unicast. So if I'm sending from host A to host B, that's a unicast frame. Destination yangu ndeiyo. Then broadcast frame, OFs, multicast frame identified by ACO bit 8th bit error rinofana kunge rina 1. I think the most common multicast frame is the IPv4 multicast frame. I've seen this one on a number of my questions. It's usually as this one. 01, it should be 05, 05, 00, no. I know it's 5E. It should be 00, I'm not so sure here. It should be 01, 01, 00, 5E. Here in the prefix multicast if it's in IPv4. Ukangoona this, it basically means that's a multicast prefix for a IPv4 address. We have multiple multicast addresses, IPv6 in a prefix yayo. Then, all right, overview of Ethernet switches. I can see 10 maybe less than 1 minute. One more session, I think we'll be done. Ikakata, use the same link to join. Typical architecture of a campus network. What defines a campus network is probably starting point. Okay, overview of Ethernet switches. Campus network, I think it's very important to define what is a campus network. Its architecture. Right? A campus